might take some time, or it will not be a very good solution approach to solve this problem. So this is one takeaway from this exercise. Okay. Now, how should we approach this problem then? So when I'm saying it is not a good method to solve this problem, what should be the approach? So you should think about whether to find an algorithm, or maybe to find a way to tell whether tracing this diagram is possible or not without a brute force method. So if you try all the paths which are possible and then you conclude, it will take a lot of time for you to conclude that it is not possible to trace this diagram. So is there a better way to tell whether this diagram is traceable or not? So these kind of questions should come in your mind. Another question which should come in your mind is, if the answer to the first question is yes, it is possible to trace this diagram, what should be a solution to this problem? Why I'm saying what should be a solution to the problem? Because there can be multiple solutions to the same problem. So for this example, I have shown you one solution. There can be multiple solutions to this problem. Okay. So these are the two questions you should these are the directions you should think about when approaching a problem. So you can be asked for any generalization of this problem, and you should have a solution method to solve that general problem. And you should think about, if that is possible, what should be a way to find a solution to that problem. Now I have kept three motivating examples, and they are interlinked with one another. So this is another motivating example. So first was a diagram tracing problem. So this is an interesting problem, which is known as Konigsberg bridge problem. I may not be pronouncing it correctly, by the way. So in 1700s, the residents of the East Persian city of Konigsberg wondered. So this is the actual city. So it had some land masses, and there was a river flowing through the city. And the land masses were connected with 7 bridges. So I have labeled the bridges 1, 2, 3, 4, 5, 6, 7. There were 7 bridges. So the resident of the city wondered if it is possible to take a walking tour of the town, crossing each of the 7 bridges. So there are 7 bridges. They wanted to take a walking tour of the city such that they cross each of the 7 bridges exactly once. So they were wondering if it is possible or not. And this problem was posed to Euler, and he came up with a very elegant solution to this problem, which we're not going into right now. But we are seeing how to approach this problem. So what we'll do is, this is a real world problem, and we will abstract this problem. We'll remove unnecessary details from this problem, and we'll model it using network models. Okay. So what are we doing is, these are the land masses. So this is landmass. This is landmass, I guess B. This is A. This is C, and this is D. So these are the labels I have given to the land masses. What we are doing is, we are using, so these land masses are nodes in a graph. So we are saying this is A, this is B, this is C, and this is D. So we have made these land masses as nodes. We have removed many details, that these are land masses and many other details. We have just abstracted the land masses to nodes. And these bridges, we have abstracted. I am not using the correct word. So we have done abstraction to make these as edges. So you see, A is connected to B via 1. So A is connected to B via 1. A is also connected to B via 2. So I have made the diagram over here. Okay. So this is the diagram. Now you see, this is a simplifying model. This has simplified the problem a lot. You have removed unnecessary details, and you are just focusing on what is relevant. You want to, so you can read the question again. It is saying you want to travel each of the bridge exactly once. And you see, this problem is very much similar to the previous problem. You're trying to trace all the edges in this graph without jumping from one landmass to the other, which you cannot do in real life for this problem. And you're not allowed to retrace back that same path, right? So this problem and the previous problem which we saw is very similar. This problem, and actually it is exactly the same problem, but one application I have shown you. Okay, so these two problems are the same, exactly the same, when we have modeled it as a network model. So this is what it is known as a network model. And the question again remains the same. You are asked to find a path starting from any node come and trace all the edges exactly once. So there are constraints to this problem. There are two constraints. First, you cannot travel an edge twice. And the second constraint is you cannot jump from one node to the other. Okay, cannot jump from one node to the other. These are the two constraints for this problem. And you notice one thing: if you find any solution to this problem, that becomes the best solution to this problem because there is no objective function. It is not saying that you have to minimize the distance or something like that. There is no objective function to this problem. This problem just has constraints, and you are asked to satisfy these constraints. Okay? Any solution to this problem will be the best solution to this problem, or in other words, it will be the optimal solution to this problem. I hope it is clear. All right. So we'll see one more example, which is known as the Chinese postman problem. So you can read the problem. So it says a Chinese postman wishes to travel along every road in a city in order to deliver letters with the least possible distance. So I have given you the graph of that city which he wants to travel. And the question the postman is asking is, he wants to travel every node, every road with the least possible distance. So this problem and the previous problem, there are some similarities and some differences. So can you take a minute or two to think about what are the similarities of this problem and the previous problem and the differences between this problem and the previous problem?
It is only mentioned that we have to traverse every road in the city. So it is not mentioned whether we have to traverse them exactly once or more than
Right.
once.
So one difference is there's no restriction on traveling a road twice. You can travel a road. Yes, just a minute. A road twice. Yes, go on. Who was it?
Yeah, it is different saying that with the least possible distance. That is the difference
Yes.
between this and the other problem. Yeah.
So there is an objective in this problem. There's an objective to accomplish. You can get some distance. So one trivial example can be you just go here and come back, then go here and come back, then go here and go here and then retrace the path, go here and come back, go here and come back. So this is also a solution. Why? Because you are allowed to travel the road more than once. So this is also a solution to this problem, but it will not be a good solution. Why? Because the objective is to minimize the travel distance. Therefore, any feasible solution to this problem will not be an optimal solution to this problem. You have to find that path such that the objective, which is the total distance traveled in this tour, is minimized. So this problem has an objective to fulfill or satisfy. Is that all right?
Yes, sir.
Yes, sir.
And both of the problems are similar in the sense we are trying to cover all the roads, all the constraint, all the edges. Okay. So what are the constraint to this problem? The constraint to this problem is you have to travel all the roads, travel all the roads. So you cannot skip a road. And another constraint to this problem is you cannot jump from one node to the other. You have to take an edge from one node to the other. You cannot jump from one node to the other. Okay. So these are the two constraints for this problem. And you are required to minimize the total distance traveled in this loop. Yeah, so I have completed this slide. Now some applications. You see, we have started with a very toy problem and we saw gradually increasing more consideration to this problem. And now you will see that these kind of problems are actually found in real life with more constraints. Okay, so you can have more constraints, but the basic problem will remain the same, okay? May remain the same. So for example, robotics and path planning. So if you have a robot, that cleaning robot which are sold in Amazon these days, these cleaning robots actually optimize the distance it is traveling in the uh, home floor to clean the whole floor. So these kind of robots are using such kind of problems to solve and using algorithms to solve this problem. Navigation of automated guided vehicles in warehouses. So if you have a warehouse where there are lanes and both the sides there are almirahs or shelves, and these guided vehicles will optimize the distance it is traveling such that uh, it can access all the shelves, but it can go around and cover all the paths in the warehouse. Another example can be network routing and telecommunication infrastructure, enhancing telecommunication routing protocol to minimize latency bandwidth using while also optimizing fiber cables. So you are asked to lay fiber cables from one city to the other. What should be the least amount of fiber cable used, and so on and so forth. Or maybe you already have cables laid down between some cities, and you are trying to send some signal from one city to the other, or you are sending some signal which is required to be sent from all the cables. So what should be the path of that signal? Something like that. So these are examples. It can be a variation of this problem, but I'm showing some applications. Transportation and logistics. So for example, a newspaper vendor is trying to find a path to such that it can deliver newspapers to all the house in the lanes he has to travel. Urban planning. So it can aid efficient pathway and public planning. For example, garbage collection. So there are trucks which collects garbage in all the lanes in a city. So it is trying to find the minimum distance he has to travel. The vehicle has to travel, and he has to collect all the garbage. Street cleaning is also an example. In foreign cities, there are snow clearing machines. So that also requires to clear the snow in all the lanes. So these are examples. And drone surveillance also. These are some motivating examples. Now we'll proceed to the second portion of this session. So is it clear? These are some examples. Is that clear? Yeah.
Yeah.
Okay. So what is optimization? Optimization is the process of finding the best solution from a set of possible solutions based on some defined criteria. So you can have one criteria or you can have multiple criteria, but you're trying to find the best solution which suits that criteria and satisfies some constraint to this problem. So more technically, optimization is the process of identifying one or more solutions that achieves the best possible value of one or more objective such that you're satisfying all the constraints. So you see, there are few important terminologies, or not terminologies, terms in this definition. One or more objectives. So your problem can have one objective or multiple objectives. And if you have multiple objectives, you should have a technique to handle those kind of objectives. And best possible. So what happens is in some problems which are very difficult, you are not looking for the global optimal solution. You are so you are satisfied with good enough solutions. So that can also come in. But in optimization, we look for the best possible solution. And why I am saying one or more solutions. So you see, sometimes the global optimal solution is not just a single solution, it is a set of solutions. So you may be looking for multiple optimal solutions if it is present in your problem. What is the aim? The aim is to achieve the best possible performance under a given circumstances. So these are preliminary definitions. So two important spaces. One is known as search space and the other is known as objective space. So in this here, I have shown you a search space with two dimensions. So what is a search space? A search space is a set of all possible solutions for an optimization problem. So if you have two variables, x and y, and both are real valued, so you see this will be the search space, the first quadrant, if both the variables are non-negative. So I have drawn the search space over here. And what is an objective space? So for each point in the search space, each feasible point in the search space, that will correspond to a value in the objective space. So you have an objective function f of x or f of capital X, where capital X is a vector. It takes a solution from the solution space and produces over here, it produces a scalar because it is a one-dimensional objective. And if you have a maximization problem, then you're looking for a solution which maximizes the objective. If it is a minimization problem, then you're looking for a solution which minimizes the objective. So this is what is known as a search space and an objective space. Your objective space can be of more dimensions if you have a multi-objective problem. So for example, if you have a bi-objective problem where you have two objectives, then this will not be a single line, it will be a two-dimensional graph. Okay. Any questions?
So, like in the Chinese Postman example, the list distance to be covered, that is the objective space.
So over there, the objective is just to minimize the distance, and distance is
Yeah,
a scalar. So it will be a one-dimensional space, objective space.
one dimension. Okay. Okay.
So bounds in the objective. So this is a very important term, bounds, and you will hear this term again and again in the summer school. So you should be familiar of this term bound, lower bound and upper bound, and we'll discuss about this now. So in optimization problems, a bound is a limit on the value of either a variable or an objective function. More importantly, we will focus on objective function bounds. Okay, so a lower bound and an upper bound. So we will see what these bounds are. Okay, so let us focus our attention on optimization problem of maximization type. So we have a maximization problem, and we are looking for we are looking on a problem of single objective. So it is a single objective problem. All right. So we have seen for a single objective problem, the objective space is just a line. So I'm just drawing a line extending from minus infinity to plus infinity for the time being. Okay. Now you see, we were talking about feasible region. So I have not shown you what a feasible region is, but a feasible region is that, so the solutions which are feasible. So if you have a problem, so suppose this, any problem, I'll not give you some examples. So if you have a problem and if you find a solution which satisfies all the constraint, that solution is known as a feasible solution. I'll repeat again. So if you have a problem and any solution which satisfies all the constraints of that problem is known as a feasible solution. What is a feasible region? The set of all feasible solutions is forms the feasible region. Okay. So you see what I'm telling you. So suppose this is a maximization problem and this is the global maxima, Z star. This is the global maxima. Okay. Just give me a minute. I'll draw again. So this is Z star. For a maximization problem, we are looking for this value, the maximum value which we can have for a given problem. And we know what is a feasible solution. Okay. Feasible solution. So suppose x1 is a feasible solution, and this is a vector for the time being. So you are looking at a solution x1 which satisfies all the constraints. You plug this solution to the objective function and you obtain that this is the value of x1. Because you're trying to maximize the objective function value, this feasible solution can either be over here or lie in this region. Any feasible solution will either match the maximum objective function value attainable, or it will be below that value for a maximization problem, right? Is that clear? Any feasible solution will either be exactly same as the optimal solution, optimal objective function value, or will be less than that. All right. So these solutions in the objective space is known as a lower bound. Any value lower than the optimal objective function value is a lower bound. And any value above this optimal objective function value is known as upper bound. Now, why is this important? You see, first thing to note is that if you have a way to obtain a lower bound and an upper bound, and your upper bound matches the lower bound, then you know that that solution is optimal solution, because your upper bound and lower bound, the optimal solution value will always lie between the upper bound and the lower bound, right? Your optimal solution will always lie between the upper bound and the lower bound. So if upper bound and lower bound matches, you know exactly the optimal solution to this problem. Now there are techniques to find upper bound. So suppose you have a problem. I'll specify the problem as maybe P1. There's a problem P1, and you have a technique to obtain upper bounds to this problem, and it is a maximization problem. So one upper bound algorithms give you, suppose, UB1, and another upper bound algorithms gives you UB2. So you see, the lower the upper bound, the closer you are to the optimal solution. So you will prefer that algorithm which gives you the lowest upper bound. Is that all right? And it is same in the other end also. So you are looking for an algorithm which can give you the highest lower bound. And in a maximization problem, all feasible solutions gives you a lower bound. All feasible solutions in a maximization problem gives you a lower bound. So let us see the same thing in a minimization problem context. So again, since it is a single objective problem, we'll have a linear space for the solution, objective space. And this is the Z star, which is the optimal solution to this problem. Again, since it is a minimization problem, any solution, any feasible solution will have an objective function value in this region. Either it will be same as the optimal solution, optimal objective function value, or will be more than that. And any feasible solution will give you an upper bound for a minimization problem. Any feasible solution will give you an upper bound. And if you have algorithms which can find lower bounds, so you are looking for that algorithm which gives you the highest lower bound or the maximum lower bound. Okay, so these two concepts are very important. For a maximization problem, if you're working with the upper bounds, you're trying to find that algorithm which gives you the minimum upper bound. And if you're working for a minimization problem and you have algorithms to find lower bound, you will try to find that, you will use that algorithm which gives you the highest lower bound, because you're trying to reach the global optima. You're trying to reach that global optima. Okay, so these two terminologies will be repeated again and again in the large scale optimization summer school. So please be clear on this. Is that all right?
Yes, got it.
Yes, Zach. I am sorry if I'm not pronouncing it correctly.
No, you're good. You're good. No, continue. That was an accident. Go ahead.
Okay.
I answered my own question. Thanks.
Okay. So no, why can this help? Because it can help you with termination criteria. So if lower bound and upper bound has a difference of 5% or so, or maybe it is exactly matching or something like that. So it helps to give you a termination criteria. Or it can also give you the quality of the solution. So suppose if your upper bound and lower bound are very close to 2% or 5%, then you know then that the solution cannot be worse than 2%. It cannot have an optimality gap of more than 2%. So these are two key, I'll not say insights. These are the things you can derive from lower and upper bounds, or maybe uses of lower and upper bounds. There are other uses also. I've just given you two examples. Okay. So I have completed two sections of my slides. First was some motivating example, and the second was basics of optimization. Yes, you can ask.
So when you say optimality gap, can you define optimality gap? How
Yes,
do
I
you
can
know?
define.
Yeah, sure. Thank you.
I can define what an optimality gap is. So you see, this is a indicator, performance indicator, which says how good your solution is, and you can define your own performance indicator. Okay, so when I say optimality gap, what I am saying an optimality gap is may change depending upon what another person is thinking. So, but if I say optimality gap, so it means upper bound minus lower bound. So difference between the upper bound and lower bound by, so this denominator will typically depend upon whether it is a maximization problem or a minimization problem. But generally, what people write here is the objective function value of the feasible solution. So if it is a minimization problem, any feasible solution will give you an upper bound. So you can write here upper bound. And if it is a maximization problem, you can write here lower bound. But it depends. So if I am incorrect, so Professor Yogesh is also here, he can pitch in. But this is what it means by optimality gap into 100%. Professor Yogesh, am I telling this correctly? I hope I am.
Yeah, I think it's fine. Actually, the gap, you see, since we don't exactly know where the optimal solution is, but we certainly know it is somewhere between upper bound and lower bound. Okay, so it is the difference between the upper bound and lower bound as a percentage of some standard value, either the lower bound itself or the upper bound itself. which tells you how, at the most, how many percentage points away you can be from the optimal solution. So if you take a numerical example, suppose my upper bound is 110 and lower bound is 105, optimal is somewhere between 105 and 110, but I don't know where it is. But I can be sure it is no more than 4 or 5% away from the optimal, because the difference between the upper bound and lower bound is within 5%. Does that make it clear?
Yes, Professor. Thank you.
Yes, sir. Thank you, sir. Okay, so we are moving on to examples of problems, and we'll model it using different models. So first we will see an example of integer programming model, and not integer programming, sorry, linear programming model. And I have taken very simple examples, but this will just give you ideas of what kind of variables are used and how different problems are modeled using these kind of modeling frameworks. Okay, so first is a diet problem. Think about that you have food. So I have a table over here. So you have two foods, food one and food two, and each food has some amount of calories in it, some amount of protein, and some amount of vitamins. And you are interested in only these three macro and micronutrients. You are only interested in these three nutrients. And what you are trying to do is you are trying to mix food one and food two such that your requirement, whatever your requirement is fulfilled. So for example, you want to have calories of at least 500 kilocal. So you want to have that amount more than equals to 500. Protein more than equals to 50 grams. Vitamin C more than equals to 30 grams. By the way, these are made up examples. So if it is not correct in real life, please don't ignore. Okay. So again, I'll give you the problem. So the problem says you have two foods. You have to take these two foods in that proportion or quantities, food one and food two, such that you meet the requirement. So this is the constraint. You are actually eating these two foods such that the constraint is such that the requirement you have in your mind is satisfied. But there is an objective function value. So if you think if this problem doesn't have an objective function, you can consume as much quantity of food one and as much quantity of food two you like. You can consume 100 kgs of food one and 200 kgs of food two, and your requirement will automatically be satisfied. But there is an objective function. If you consume that much food, you have to pay for that food. So the objective function is to minimize the cost. So the objective is to minimize the cost, and that actually leads to finding that optimal point where the quantities of food one and food two is such selected that it meets the constraint and gives a good solution such that is the objective is minimized. So this is a minimization problem. Okay. All right. So you know what the problem is. Let us model it. So before that, you have to think about some variables, decision variables, the variables which you will use to find the quantities of food one and food two. And before we discuss upon the decision variable for this problem, I'll just tell you that for a given problem, you can have different kinds of decision variables. So it is not that all problems has a particular set of decision variables. Some problems can be modeled in a better way when different kinds of decision variables are used. So finding good decision variables, and these are art. So you will learn when you do more modeling. Okay. So for this problem, the decision variable is very simple. You can just unmute and tell me what should be the decision variable. Sorry.
Yeah, it's a decision variable is the units for this problem. How
Yeah,
much
so
it? Yeah.
So the quantity of food one and quantity of food two. So the decision variables are units of food one. X1 denotes the quantity of food one, and X2 denotes the quantity of food two. So you see, when you purchase X1 quantity of food one, and each unit of food one costs $3, then you will have 3x1 as the cost for the quantity purchased for food one. Similarly, 2x2 is the cost for the x2 unit of food two purchased. So we are trying to minimize this function 3x1 plus 2x2, but there are constraints. What are the constraints? You see, for food 1, 400 kilocalories are in 1 unit of food 1. Similarly, 200 kilocalories are in 1 unit of food 2. So you have 400x1 plus 200x2 is more than equals to 500. Similarly, you can write the constraint for protein, and similarly, you can write the constraint for vitamins, vitamin C. And these quantities cannot be negative, so you are giving a non-negativity constraints. So x1, x2 is greater than equals to 0. And this is what is known as a linear programming formulation. Why? Because the objective has linear, so the function is linear. You don't have any multiplication. There is nothing in the exponent of one variable or the other. The constraints are linear, and the decision variables take continuous values. So linear programming should satisfy these three conditions, which I just listed down. The objective should be linear. The constraint should be linear. It should have a greater than equals to or less than equals to sign. And the decision variable should be continuous. Is that okay?
Yes.
So if that is okay, we will move on to the second problem, which is work scheduling problem. So I'll describe the problem. So there is a maybe a hospital, and the hospital requires nurses, and each nurse has a 5-day consecutive 5-day shift. So if a nurse starts on Monday, her shift will end on Friday. She will not come on Saturday and Sunday. So it is a 5-day consecutive shift followed by 2-day off. What is the objective? The objective is to minimize the total number of nurses employed while meeting the daily nurse requirement. So each day has a requirement of nurse. Monday has a requirement of 17 nurses. Tuesday has 13, and so on and so forth. These quantities are listed in this table. Okay? So the objective is to minimize the number of nurses you are employing such that you are meeting this requirement. Actually, before we move on to formulate this problem, can anybody tell me a upper bound? It may be a very bad upper bound, but can anybody tell me what will be the upper bound to this problem? What it means is a value. If you keep that number of nurses, all the requirements are satisfied.
19.
19. Sir.
Why do you think 19 will be a solution to this problem, upper bound to this problem?
Because
if you
19 number was every employee, so all the days we can work, right? That
No,
the requirement already.
these nurses have a 2-day off. So if all the nurses are employed on Thursday, 19 nurses, they will work on Thursday, Friday, Saturday, Sunday, Monday, Tuesday and Wednesday will be off. So you won't have any nurse on Tuesday and Wednesday, right? So 19 is
Yeah.
incorrect.
A very bad upper bound would be just add them all the requirements.
Yes, that is a very bad upper bound, but still a valid upper bound. You can just add all the requirements and that will give you a upper bound. So you have a method to find an upper bound to this problem. You can have other methods. So you see, one upper bound is you add all these 13 plus 17 and so on and so forth till 11. So this is UB1. And since it is a minimization problem, we are trying to find that upper bound, which is minimum, right? Minimum upper bound. So can we find a better upper bound to this problem?
We can just add 19.
19 plus 11
Sum of
19
3, top 3.
plus 11.
19 plus 11. I don't think it will work. So if you are 19, so this will
15 plus 15. That would be
19 plus 15. So you see, if you have 19 nurses, sorry.
Yeah, that's what I was saying the same.
Yeah, so if you have 19 nurses, all can start on Thursday. So this is covered, this is covered, this is covered. Until Monday, you are covered. So you require 15 more nurses for Wednesday. And if you have 15 nurses, you can also satisfy Tuesday's demand. So you can have another upper bound 19 plus 15 as UB2. And you see UB2 is strictly better than UB1, right? So any optimal solution an optimal solution to this problem will always be less than UB2 or equal to. It will be less than or equals to UB2.
Hello. Actually, I have
right?
a doubt. Yeah, I have a doubt. So, like you said, 19 plus 15. So, like, let's suppose all the nurse work on Wednesday. From Wednesday, Thursday, Friday, Saturday. So it would be 5 days continuous and 19 we are starting. So then again Tuesday, Wednesday remains. So the problem is that 13 gets affected again.
No.
So on
So
Tuesday,
you see, if you
no,
have
no,
nurse 9, yes, continue.
you know, I'm saying like if you are taking Thursday, 19, Thursday, Friday, Saturday, Sunday, Monday, 5 days satisfied, good enough. If you are starting from Wednesday, Wednesday, Thursday, Friday, Saturday, 5 days come. So the Tuesday is remaining 13. So 30 to 13 also becomes an off. Actually, it should be like the sum between the two maximum or two minima, basically in between days. So like
So
it should
what
be
you are
some
trying
13
to,
plus 19.
right? So what you are trying to do is you are trying to come up with an upper bound, right? You are trying to come up with a better upper bound than 19 plus 15. So that is what you are doing, right? You are trying to come up with a
Yeah.
better upper bound. So
Better
that can
upper
be done.
bound.
We can debate here and there, and we can debate. So I'm just saying these two are upper bounds. You can have better upper bounds as well. Whichever is the best upper bound, the minimum upper bound becomes the best upper bound. That is all right.
Yeah. All right.
Okay. All right. So let us model this problem. So I would ask you to give me a decision variable for this problem. Okay. Try.
It can be number of nurses working on a particular day.
Number of nurses
working on ith day. I vary
number
from
of
Monday to Sunday.
nurses working on day I, where I equals to 1, 2, 7. Is that all? Is that correct?
Yes.
Okay, so let us write the objective function. So what will be the objective function then? First, let us write the constraint, because first let us write the constraint. So what will be the constraint?
So 2 days off for each nurses.
No. So if you have these variables, xi denote the number of nurses working on each day. So how will you write the constraints? So how will you write these?
7 constraints.
Yeah.
Okay. So
for each day.
Please tell at least one.
X1 less than 17.
Greater than equals to. So you want at least 17 nurses.
At
right?
least, yeah, greater than.
Greater than 17 and so on and so forth, right? So you have the constraints. X1 greater than 17, X2 greater than 13, and so on, and greater than equals to 13, and so on and so forth. Is that all right?
Yes, sir.
Okay. Now what will be the objective function? How will you write the objective function?
Minimize X1 plus X2 plus X up to X7.
Okay. So you are saying minimize X1 plus X2 dot plus X7. Is that correct?
Yes.
Please check again. Is that correct? Yes, you can unmute yourself and speak. I don't have any issue.
So decision variable needs to be changed, I think. So it could be that xi could be representing number of nurses starting on day I.
Okay, xi could be number of nurses starting at day I. I'll come back to you. Just I'm asking again. Is this objective function correct? So you can just say yes if you feel it is correct.
No, it's not.
Okay. So some are saying no and others are just not responding. So I guess they are saying yes. Okay. So you see, this is not exactly capturing the number of nurses working employed. So what is the objective? The objective is to capture the number of nurses employed. So when you say number of nurse X1 represents the number of nurses working on day 1, that is Monday, and you're saying X2 is the number of nurses working on day 2, which is Tuesday. If you add 17 and 13, if you add 17 and 13, not 17 and 13, X1 and X2, then you see you're double counting some of the nurses, because that will not represent the number of nurses, number of employed nurses. Is that correct?
Yes,
if I add X1 plus X2, this will not exactly capture what we are trying to capture. And if I write ... X7, is that correct? It is not exactly capturing what we are trying to capture.
Because one
So
nurse
either
is repeating
Yes,
data.
nurses are getting repeated.
Yeah.
So what we have to do is either we have to come up with a different sets of decision variable, or we have to find a way to write the objective function value using this decision variable. Okay. So there are two ways you can go about it. Either you have to use a different set of decision variable, or you have to find a way to write the objective function using this set of decision variable. So I'll not do the second thing because I have also not tried how to write the objective function value using this set of variables. Maybe there is a way, maybe there is not. I don't know. Maybe you have to introduce more variables to write the objective function value. But this is one set of decision variable which will help you formulate the problem. So who was speaking? Please, you can unmute and speak.
Yes, now
Yeah.
objective can be sum of all these numbers.
Yes. So you see, what is the decision variable now? The decision variable is xi denotes the number of nurses whose work cycle starts on day I. So if I write x1, it represents the number of nurses whose work starts on Monday. So if I write I is equals to 1 as Monday and I is equals to 7 as Sunday. So whose work starts on, number of nurses whose work starts on. Okay, this is important. So you see, you will not be able to double count the nurses if you write x1 plus x2 plus dot 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 plus x7. So over here, you are exactly counting the number of nurses employed, because x1 are the nurses employed starts on Monday, x2 are the nurses whose duty starts on Tuesday, and nobody is in both x1 and x2, because if a nurse duty starts on Monday, her duty cannot start on Tuesday. So if you sum this up, it will give you the number of nurses employed. So this is the objective function. Is that all right? Now let us write the constraints. So how will we write the constraints? How will we write the constraints? Earlier constraints were simple, but now you have to think about how to write the constraints.
So you have to write
It would be x
day.
Monday plus x Tuesday plus x Wednesday, x Thursday less than some 17. The day wise we take.
Okay, so what will you do?
So like those who are
X1
working
plus,
on Monday would be x1, then
Plus.
excluding this x2 and x3, x1 plus x4, x5, x6, x7 should be less than equal to 7, greater than equal to 70.
right? So I will repeat for everyone. You see, anybody's duty who starts his or her duty on Monday will work from Monday, Tuesday, Wednesday, Thursday, and Friday. Whoever is starting his duty on Tuesday will work on Tuesday, Wednesday, Thursday, Friday, and Saturday. So you see, if you're writing a constraint for Monday, then you have to see which nurses are present on Monday. So you see, Mondays nurses are present on Monday, Thursdays, Fridays, Saturdays, and Sundays. These nurses will be present on Monday. So it will be x1 plus x3 plus x4. 1, 2, 3. No, 3 will not be there. x1 plus x4 plus x5 plus x6 plus x7 is greater than or equals to 17. Is that all right? Is it all right?
Yes.
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 Okay, so we have the objective function, we have the constraints, and these constraints will take integer values 0, 1, 2, 3, 4. And therefore, this is an integer programming problem. Is that all right?
Yes.
Now I'll tell you one thing. Yeah, any question? Okay, so I'll tell you one thing. So if this problem has a property, which when solved, so if this problem is solved using LP techniques, will give you integer solutions, because this problem has a property, and that property is known as totally unimodularity. And you will not come across this term in this large scale optimization, I guess. But I just wanted to tell you that this problem has a property which is known as total unimodularity, and because of that, you can solve this problem using LP techniques and you will get a solution. So the optimal solution will be integer solution. That is what I'm trying to tell you. Okay. All right. So we'll see one example of network model. So I have 3 more models to cover: network models and nonlinear model and one multi-objective problem. Okay. So network model. So the problem is you are trying to supply 1 unit of water. It is 1 unit of water from city 1 to city 6. But city 1 and city 6 are not connected directly. You don't have a connection between city 1 and city 6. A direct link between city 1 and city 6 doesn't exist. So that connections which are present between these cities 1 to 6 are listed in this table. So when I say infinity, it means that, so when I say infinity, so suppose you are here. So it means city 2 is not connected to city 1. Again, when I say over here infinity, city 3 is not connected to city 1. But when I'm saying 1 to 1, it just means we are not trying to supply water from city 1 to city 1. That's why I have written infinity. Okay. So over here, infinity has two meanings. Both the cities are not connected, or it is the same city. That's why I have written infinity. And these numbers, 30, 40, 20, 25, these numbers indicate the pressure loss. So if you send 1 unit of water from city 1 to city 2, it will cost you 30 pressure head, 30 units of pressure head loss. So 30 units of pressure head will be lost. Okay, 40 units of pressure heads will be lost. So this is the tabular representation. And what is your objective? Your objective is to send 1 unit of water from city 1 to city 6 such that there's minimum loss in pressure. These represents pressure loss, 20, 30, these numbers represents pressure loss, and you're trying to send 1 unit of water such that the head loss is minimum. So we can model it as an integer programming problem. What you can say is you can use variables like xij. So when you use variables like xij, it represents whether you are sending water from city I to city j. So this is I equals to 1, I equals to 2, and so on and so forth. So when I write x to 1, it means if it is 1, then you are sending water from city 2 to city 1. If it is 0, then you are not sending water from city 2 to city 1. So this is the variable which I am using. And each element in this matrix is represented as Pij. So when I write P 3, 5, so you have to go over here 3 and 5. So it is 30. Okay. So Pij is a parameter which the values over here are written. Okay. And since I have written infinity, and you cannot use infinity in computer, you cannot directly write infinity in computers. You can give any large number, 1 lakh, 1 million, something like that. Okay. So how will we represent the objective function? So you see, you can just sum Pij times Xij, and you sum over all. So what are you doing? You are summing this times. So X11 times P11, then this and this, and you're summing all those up. Whenever X11 becomes 1 or Xij becomes 1, that Pij will take value, and otherwise it will not take value. So what are we doing? We're summing across all the elements multiplied by the Pijs. So this is how I'm writing the objective. Is that all right, or am I going fast? The objective function is clear, right? I hope it is clear.
Yes, sir.
Okay. And the constraints. So this is just a flow balance constraint. So if you are sending 1 unit from one city, so if this is the node or a city, suppose city I. So if something is entering, it must leave that city. So you cannot accumulate anything there. Okay. Only two exceptions are there: the source node, city 1, and the sink node, which is city 6. So in source node, there is only exit of 1 unit, and in sink node, there is only entry of 1 unit. Other than that, all the cities should have a flow balance. 1 unit of entering and 1 unit of exit, or no entry, no exit. Is that all right? Okay. So for city 1, I'm writing summation of xi1. So what is I1? Any edge entering 1 from I, from city I. So it is written as xi1. And I'm summing it over I1 to 6. It is 0. And from city 1 to j, any j will be 1 because 1 unit is exiting city 1. So you can write it like this, or in another way, I'll show you. You can just subtract it. So this minus this is equals to -1. So what you can do is I equals to 1 to 6 xi1 minus summation of j equals to 1 to 6 x1j is equals to -1. So you can write like this also. These are just flow balance constraints. I guess if you have come across these kind of problems, so you know what flow balance constraints are. So similarly, we will write the constraints for city, any intermediate city and the source sink city. So for the sink city, it will be like this. And for the other cities, it will be sum of one minus sum of the other is equals to 0. And I have given a non-negativity constraint. You can also write it as xij belongs to 0, 1. I should have written that. This is my mistake. It should be xij belongs to 0, 1. So this is incorrect actually. So this is the problem. I'm trying to minimize the objective function such that, so this is written in a compact form. So it is saying summation of xi to k, I equals to 1 to 6. So k is the focus city. So when I say k, you are trying to focus on city k. So when I sum this up, it means all the edges which are entering k, this sum minus all the edges which is exiting k. So it is summation of x kj, j equals to 1 to 6. This difference will be minus 1 if it is the source city. This difference will be 1 if it is the sink city. And this difference will be 0 if it is any other intermediate city. And again, this is an error. It will be 0, 1. Okay. So notice we are using n square variables, I comma j. So it is n square variables. If we model this as a network model, then it becomes simpler. Over here, I have drawn the network model. There are edges and there are nodes. So what is a node? So these are nodes and these are edges. Okay. So since we know exactly what is the pressure loss between the cities, I have the table over here. So whenever there is infinity, we will not draw a path. And whenever there is a number, we will draw that path and write that value in that path. So you see, city 1 is connected to city 2 with a head loss of 30. So that is what I have done over here. City 1 is connected to city 2 with a head loss of 30. So we have a network model and there are approaches to solve this problem. There are algorithms to solve this problem. In exactly, actually, it solves optimally. So what are we trying to do is we're trying to find a path from city 1 to city 6 such that the head loss is minimum. So it is kind of a shortest path problem. You have to go from city 1 to city 6 following a path such that the cost is minimum. It is the shortest path problem. Is that all right? Is that all right?
Yes.
Is
Okay.
there a requirement that we should cover all the nodes?
No.
Okay.
You have just to reach from city 1 to city 6. Just have to reach from 1 to 6. Okay. So this is a drone delivery problem, and it is actually giving you an example of a nonlinear problem. Okay. So I'll give you the context. So suppose the region is in a 2-dimension square. Okay. So the first quadrant, the region is first quadrant. And each point can be represented as A comma B. A comma B. Okay. So a food delivery company is contemplating the installation of a drone delivery facility in a city of n divisions. So why n divisions? Just think about the grid graph. There are n divisions located at A1, A1, B1, A2, B2, so on as A and Bn. Okay, so these are points where there are demands. So these are the points where demands will come. A1, B1, A2, B2, A and Bn. These are the points where demand will come. The annual delivery loads are expected to be D1, D2, and Dn. Okay, so for A1, B1, the demand will be D1. For A1, B2, A2, B2, the demand will be D2. So these are expected demand. Okay. So where should the facility be located? So these facilities, it is asking where should it be located in this 2-dimensional region? Where should it be located? So as the total delivery cost is minimized. So you're saying in this 2-dimensional region, where should I locate that facility? Where should I locate that facility such that the total delivery distance is minimized? And how will we obtain this delivery distance? It is actually proportional to the total distance traveled. So the distance between this location and the different demand points. Okay, these distance. So it is proportional to the distance traveled and the load carried. So these values d1, d2, and dn. So this is the problem. But there is one constraint. What is the constraint? In this region, in this two-dimensional region, there is a lake, circular lake. And this facility cannot be located inside this lake. You cannot locate this facility inside this lake. So that is one constraint for this problem. So there is only one constraint to this problem. What is the constraint? That facility cannot be located inside this lake. What is the objective? The objective is to find a location for this facility such that the total delivery cost is minimized. Delivery cost to these points, A1, B1, A2, B2, and so on and so forth. Is the problem clear? Is the problem clear?
Yep, yep.
The center of the lake is P, Q, and the radius is R. Okay. Okay. So
I have one question. A quick question there. So basically, that A1, B1, is it always in the intersection of the two divisions, or it can be anywhere in between those lines as well?
So these are locations of demand points. It can be anywhere in the space.
It can be anywhere in the space. Okay. All right. Thank you.
Okay. So let us see. So I had left some space to draw the same thing over here. Okay. So what are the decision variables over here? We are just trying to find one point. So we'll say x comma y. The coordinates of that point are my decision variables. So x is the x coordinate and y is the y coordinate. There are two variables for this problem, x and y. Okay? So you're trying to find x and y, two values, and it is a continuous variable. So x comma y can take any value between can be anything greater than equals to 0. It can be anything, right? Now, what is the objective? You see, this delivery cost. First of all, it is total delivery cost. So you will have to sum between city 1 to city, delivery location 1 to delivery location n. So you have to sum it for all the delivery locations. Now you see this delivery cost is actually proportional to two things. First, the distance between the delivery location and the city and the load it is carrying. So you see the objective is actually proportional to di, the distance. Not distance, sorry. Di is the load it is carrying from the location of the facility to ith city, di, and it is proportional to the distance. So we can get the Euclidean distance between two cities, which is obtained as square root of x comma ai whole square plus square root of plus y comma bi whole square. So this is just the Euclidean distance, and we are summing it up from city 1 to city n. Okay, is that all right? So this is the objective function. Is the objective function clear? So we are multiplying the load times the distance, and we are summing it up for all the n locations. Is that clear? Yeah. Yes. So this is the objective function. You see, this objective function is actually non-linear. There is a square and a square root. Sorry. What is the constraint? So constraint is only one constraint is there. This facility, which has a location of x comma y, this x comma y cannot be inside this lake. So what does it mean? It means that this distance between x comma y and p comma q, this distance has to be more than r. If the distance between x comma y and p comma q is more than r, you are sure that that location will be outside the lake. Is it clear?
Yes.
Right. So I'm writing that constraint over here. The distance between x comma y and p comma q is greater than equals to r. So this is the entire formulation. This is the objective function. Objective function is also nonlinear. The constraint is also nonlinear. And the decision variables are continuous. Okay. Now you see, for a problem to be labeled as nonlinear problem, you don't need both the objective function and the constraint to be nonlinear. If either of the one or both are nonlinear, then your problem is nonlinear. Is that all right?
Yes.
Okay.
So please repeat, sir.
So I'm saying for this problem, both the objective function and the constraint both are nonlinear. It need not be, it is not necessary. If either your objective function or the constraint is nonlinear, your problem becomes nonlinear.
Okay, anyone non-linear, then it's non.
Yes,
okay.
or both. Right?
Okay, okay.
Okay.
Sir,
So
in
this
this
is my
case,
last
both are
problem.
nonlinear.
In this case, both are nonlinear.
So I have a question on the previous. Can you please go back to the previous slide?
Yeah, I am here.
And then before this, here the supply. Why should we calculate the distance from every supply node to all of the demand nodes? Like why? Because it is we are placing the supply points to be such that it can service only a few local deliveries, right? So every corner supply need not fulfill the load of other corners, right?
So in this problem, I think I have not mentioned, but you have to supply to all the locations from 1 to n. You cannot skip a location.
Okay, all right.
Okay. All right. So this is the last problem. This is a multi-objective problem. So there are more than one objectives. And I'm sorry, it is close to 7:30. I'll take 5 or 7 more minutes. Okay. So this problem, we will see that your problem can have more than one objective. So let us understand this problem. So there is a car manufacturer who wants to reach different customer segments via television advertisement. So the mode of reaching customers is advertisement in televisions. Okay. So there are different programs. There is a sports program, there is a movie program, there is a news segment, and there is an entertainment segment. And the cost of advertising in different programs is different. So if you want to advertise in sports, you have to pay 50 lakh. If you want to advertise in movies, you have to pay 40 lakhs. And for news, it is 20 lakhs. And for entertainment, it is 30 lakhs. So this is fixed cost. You have to pay this much. Now, when you advertise in sports, you will reach 2 crore high income family, 5 crore mid income family, and 7 crore working individual. Similarly, if you advertise in movie segment, movie program, then you will reach 3 crore high income family, 7 crore medium income family, and 5 crore working individual. Is that all right? Is the data clear?
Yeah, yeah.
Okay. And there's a budget. Yes.
We have this working individuals and mid-income family, high-income family, but then working individuals, okay, sir, got it. I actually had a doubt because working individual means it will refer to one person. So I thought that was the confusion. I got it.
Now, you see, these are just made up names. You can have anything over here. You have to focus on the problem. All right. So for the time being, imagine that there is no people common between high income family, medium income family, and working individual, or are separate sets. Is that all right? Okay. There is a budget. The car manufacturer has a budget of 80 lakhs. So you see, the budget is 80 lakhs, and if he tries to advertise in all of those, then his budget will be exceeded. It has the cost will be 50 plus 40 plus 20 plus 30. It will be 140 lakh of rupees. But he doesn't have that budget. So he has to decide which program he will advertise his company or some product. Okay. So that is his decision. Now, there is one more consideration he has to think. You see, when he advertises in sports, the proportion of different individuals reached is different as compared to if he has advertised in movie. You see, when he is advertising in sports, he will reach more number of working individuals. But if he advertise in movies, he will reach more number of mid-income families. So the proportion of reach to different segments of society is different. So the decision is in which program he should advertise such that his budget is satisfied, but there is an objective. What should be the objective? So you see there are two different objectives. So I'll give you. I'll just give you. So what is the decision? Whether to advertise in sports or not. So we can have x1 as the binary variable. If it is 1, then he is advertising in sports. If it is 0, then he is not advertising in sports. So these are binary variables. So we have 4 binary variables, x1, x2, x3, and x4. There are 4 binary variables. Is that all right? if we advertise in program. So budget constraint, it is easy to write. You just sum this up: 50x1 plus 40x2 plus 20x3 plus 30x4. This should be less than equals to 80. And the domain of the variables should be 0, 1. The objective is a little bit tricky. You see, when he, so how many, so if he has these decisions x1, x2, x3, x4, what is the total number of high income individuals or families he is reaching? He is reaching 2x1 plus 3x2 plus 5x3 plus 1x4. So the solution of these variables will tell him how many number of high income family he is reaching, right? And again, 5x1 plus 7x2 plus 3x4 x3 plus 10x4, this sum will tell him how many times he's reaching the mid-income family. And again, the sum of this will tell him how many times he's reaching the working individuals. So this is one set of group, and his objective is to maximize this and this and this. His objective is to maximize all the three. Is that clear? He will try to maximize all the three. I will go on, but till this point it is clear.
Yes, sir.
Yes, sir. Now you see these three objectives are conflicting with one another because of the proportions. You see, in some cases, mid-income family has a high proportion. In some cases, lower income, high income family has a higher proportion, and in some cases, working individual has a higher proportion. So these three objectives cannot be maximized simultaneously. You cannot maximize the three objectives simultaneously. You cannot obtain the maximum objective function value of all the three with one single solution. So you have to decide how to go about it. How will you get a solution to this problem? So there are multiple ways to come to a solution to this problem. One such way is the weighted approach. So for example, you are giving more weight to a high income family. So you say this objective has a weight of 3 for me. This objective has a weight for 2 for me. And this objective has a weight for 1 for me. And then you sum it up. 3 times Z1 plus 2 times Z2 plus 1 times Z3. And that will be your overall objective that you are trying to maximize. Is that clear? This is known as weighted sum approach. So we are talking about now multi-objective optimization. Okay, so we have multiple objectives, and weighted sum approach is one way to solve multi-objective optimization problem. Another is lexicographic optimization. In that, what you do is you say, my most important objective is first objective. I will maximize that objective, and when I have obtained the maximum value of that objective, I will put it as a constraint for my second objective. So for example, this objective has a maximum value of 700. Now what you're doing is, this is your second most important objective. So you are solving for this problem, but you are saying the objective function value of Z1 shouldn't be less than 700 because that was my important objective, most important objective. I know the best value is 700. When I solve for the second objective, I will not let my solution to have a value of less than 700 in the first objective. So you're putting a constraint in the second objective when solving the second objective. That constraint is about the first objective. And then you will do the same for the third objective, and you will put two constraints, one on Z1 and one on Z2. So this is known as lexicographic optimization technique. Is it clear?
So why this term lexicographic? Can you
So it actually, I don't know exactly the meaning, but it also has another name, hierarchical optimization technique. So you are putting hierarchy in objectives. You are saying one objective is more important to me than the other.
Shubham, may I?
Yes, sir. Yes.
Yeah, I was just checking the meaning of the word lexicography on Google just now a minute ago. And it says lexicography is the science or, the art of compiling dictionaries. Okay. So in dictionary, what happens? The words come in alphabetical order A, B, C, D, right? So here again, you see, you want to put objective 1 in the first position like A, and objective 2 in the second position like B, and so on. So when there is a hierarchy of objectives, we call it a lexicographic approach. Does that make sense?
Yeah, exactly. Thank you.
Okay.
Thank you, sir, for the input. Okay, so I will not go into epsilon constraint method. So if you have interest, you can talk to me. I'll be there maybe for 2-3 days. So we can talk about epsilon constraint method. All right, so this module is complete. I will just slightly touch on solution methods of optimization problems. So broadly, if you classify the techniques of solving optimization problems, it can be classified into exact methods and approximation methods. And this classification is based on the technique you are using to solve that problem. So exact methods are those methods which will give you an optimal solution if given sufficient time. Okay. So it will give you exactly the optimal solution. Approximate methods are those methods which will not guarantee optimal, but it will give you good solutions. It will give you high quality solutions near to optima or exactly optimal, but you don't know it is optimal or not, or you don't exactly know what is the optimality gap of those solutions. But there are methods in approximation techniques also where you can get optimality gap. That is a different thing. But this is the two broad classification: exact methods and approximate methods. So in exact methods, you will talk about branch and bound algorithm, branch and cut, branch and price, which you will see in the large scale optimization workshop or summer school. There are other methods also like constraint programming, dynamic programming, A-star heuristic. So A-star heuristic is actually a kind of depth first search with some heuristic. So yeah. And in approximate methods, there are two categories: heuristic algorithms and approximation algorithms. So heuristic algorithms and approximation algorithms, there is a difference. An approximation algorithm will give you a solution guarantee. So it will tell you exactly that your solution is X% far from the optima, something like that. There will be an approximation guarantee. A heuristic algorithm, on the other hand, will not be able to give you that guarantee. Okay. And yeah, so you can further classify heuristic algorithms into meta-heuristics and problem-specific heuristics, and there you can go down and down. So this is one important thing I wanted to cover. And in this large-scale optimization course, more focus will be on exact methods, but there are sessions on approximate techniques also. Okay. So that is it from my end. Thank you. Any questions, doubts, or anything?
So,
I'll share the slides with you.
Would you like to recommend some study material for the?
So I have not kept study materials links here, but I have kept two books. One is a very well-known book on operations research, and it is freely available on the internet. And the other book which I have kept over here is a book on meta-heuristics, because I am working on meta-heuristics, multi-objective problems with meta-heuristics and so on. So I have read this book. This is a very good book. Other than that, if you want to know about more books in this relevant to large-scale optimization problems, you can come to the workshop and you will get a lot of materials and relevant resources.
Could you quickly tell us what is a meta-heuristic?
Yes, I'll tell you what a meta-heuristic is.
A very brief explanation.
Yeah, so meta-heuristic is actually a general purpose algorithm. So I'll not use anything. So it is a general purpose algorithm. What it does is it has a well-defined solution steps. And if you apply to any problem, so for example, some classification of meta-heuristic algorithms will have single solution meta-heuristics and population-based meta-heuristics. So these meta-heuristics are actually general purpose tool which can be applied to any problem. You can have problem-specific heuristic, which is particularly tuned for that problem because it is using the properties of that problem and then solving that problem. It will work worse for some problems and it can work well from particular set of problems. But meta-heuristic is a general class problem and it uses physical inspirations. It takes biological inspirations, physical inspirations, and then it tries to reach optima from starting from one or more solutions. So it will start from one solution and it will try to find a better solution or a set of better solutions. And then again from that set, it will try to find out some other better solutions. And in that way, it tries to reach global optima, but it doesn't know if it is reaching global optima. So one example can be genetic algorithm. So genetic algorithm is an example of population-based meta-heuristic where you are working with multiple solutions at a time. Another example is local search or gradient descent. So you are working with one solution and you're trying to refine that solution one after the other. So these are general techniques. You can apply to any problem. Is that clear?
Yeah. Would ant colony or simulated annealing be also be in metaheuristic?
Yeah, those are all metaheuristics. So simulated annealing is a single solution metaheuristic, and ant colony optimization is a population-based metaheuristic.
Thank you. That clears a lot. Thank you.
Yeah. My question is more of a validation than question that you were talking about multi-objective optimization, that lexicographic. Is a Pareto optimality and lexicographic both are same or they are different?
No. They are different. So I'll give you one. So what is happening over here is, so you see, when you are doing lexicographic optimization, so for example, it is a two-objective problem, and you are trying to, so this is X, I'll not write X, I'll write F, F1 and F2. So this is objective function 1 and this is objective function 2. So what you're doing is, first you are, suppose the most important objective is objective function 1, and you found the optimal value of objective function 1. So suppose this is the optimal value of objective function 1. Now what you do is you take all the solutions that have this objective function value. Now what you do is you try to meet, so if it is a maximization problem in both objective, now you will try to maximize F2 keeping F1 the same. So you will try to maximize F2 in this line. So suppose this is that point which maximizes F2. Given
it's like a non-dominated solution we're trying to take, something like that?
No. So if you are talking about non-dominated solution, so you will have like this, the Pareto front will look like this. And okay, so I'm sorry, why I'm telling you I'm sorry, because if this is the point which maximizes F2 and where F1 is maxima, so this is actually both side a maximization problem. So your Pareto front will look like this. Is that clear?
Yeah. So if it is in a maximization case, yes.
It is a 1 point because you are first maximizing one objective and keeping that objective to that maxima, you are trying to maximize the other objective. So you're not moving the value of objective function 1.
Yeah.
You're fixing that value.
Yeah, if it's a minimization case, the same front tire will come downwards.
Yes.
Thank you.
Any more doubt?
Can you talk about epsilon constraints you were saying?
Sorry, I couldn't understand your question.
Can you talk about the third one for multi-objective optimization? Epsilon constraints.
Epsilon constraints. So we don't have time over here to discuss that. So we can talk about it when we meet maybe on Tuesday. I'll come there on Tuesday.
So, sir, where can we watch this recording, sir?
So that you will get information from mail. I actually don't have information right now.
Yeah, we will share the recording over email. It will be available in your team's activity also.
Also, please share this presentation.
Okay, ma'am.
Yes, I will do that.
There are no further questions. We can thank Shubham for this session.
Yeah, thank you, sir.
Thank you, sir. It was very nice.
Thank you all for joining.
I hope you enjoyed it.
Thank you. Thanks a lot.
You will be physically present, sir, at IIT?
Yes, I will be present there on Tuesday, Wednesday, and Thursday. Thursday half day. Yeah.
Okay, thank you so much, sir.
All right, so we'll meet tomorrow for our first session on computational optimization by Guneshwar Anand. Hope to see you all tomorrow as well. Thank you, Shubham, for this informative session. Maybe we can end it now.
Thank you so much.